In this video, I'm going to present our paper, Dynamic Focus-Aware Positional Queries for Semantic Segmentation. I'm the presenter Hao Yu from Monash University. Today's agenda includes 5 parts. Firstly, I'm going to introduce positional query, which is the positional prior for the target segments in the data framework. Then I'm going to discuss whether the existing positional queries are good enough for semantic segmentation. And the answer is they are either inaccurate or cannot describe semantic regions correctly. And then I'm going to introduce our method, named Dynamic Focus-Aware Positional Queries, which simply encodes the local information for image patches weighted by the focus of each query. Next, I'm going to talk about another part of our method, which is called high-resolution cross-attention, which model cross-attention only on the informative high-resolution regions for lower costs. Finally, I'm going to discuss the quantitative and qualitative experiments, show that our method is very good. We first talk about the background for cross-attention layers in data-like segmenters. Data framework is very popular in segmentation tasks, which encodes target segments by queries. And the query is actually formed in 2 parts. One part is the content query, which preserves the semantic info for the target segments. And the other one is the positional query, which provides the positional prior. And these 2 parts are actually added together. So cross-attention models the relationship between the patches and the queries. There are actually 2 types of positional queries. The first type is positional queries as learnable weights. So the downside of that positional query is that it is often biased to training data and be inaccurate for individual samples. We can see the randomly initialized positional queries as learnable weights are actually the same for all the different blocks. And the second one is positional queries that encodes the anchor points. But however, the anchor points cannot describe semantic regions, which is the best for segmentation. In that case, our aim is to develop positional queries that specifically for segmentation with fine-grained positional priors. We next present our main method, the FPQ, which is simple yet effective. The formulation of the FPQ is on the left-hand side, which includes 2 parts. The first part is the previous attention scores, which tell us what patches do the queries actually look at. The other part is the patch positional encodings, which tell us what's the local information of these areas. So these 2 are weighted combined together with some bias and an activation function. So our DFPQ accordingly have the benefit, which contains rich segmentation cues that include fine details, edges, and boundaries, and while being lightweight. The visualization of our DFPQ is on the right-hand side. We next show the visualizations of the attention maps. We can see the attention without the FPQ is way better than the attention with the previous positional queries. We can see the previous positional queries, the attention is actually lose its focus while being scattered. While for our DFPQ, the attention maps are more precise and around the target segments, especially the boundary areas. Another part of our framework is the high-resolution cross-attention, which encodes the token affinity only on the top K informative pixels that are indicated important in the low-resolution feature maps. In this case, we can have a smaller set of keys and values, so that we can mitigate the memory and computational burden. So this is the general framework of our FA-seg, which includes the DFPQ and HRCA by making minimal modifications from the popular mass-to-former framework, but making substantial performance gain. Let's see the experimental results. We can see Our FA-seg achieves clear performance gain from mass2former and outperforms the baseline methods on all different backbones and datasets. Let's next see the contribution of both our modules by ablation study. We can see both modules contribute clearly to the outstanding performance of our FA-seg. We next show that since our DFPQ closely relates to the implementation of KP, which is the patch positional encoding, so a better KP is very helpful for our FA-seg, but not for mass2former. After that, we show that our HRCA saves much training time memory with only marginal MIOU loss on ADE20K dataset. We next show that our DFPQ is clearly better than all different kinds of positional queries, and our HRCA also beats the other efficient cross-attention methods. Finally, we show more visualizations. We can see the cross-attention maps are more accurate with our DFPQ than using the other positional queries with the same experimental settings. And we also show that our FA-seg can make accurate predictions that is closer to the ground truth and better than mass2former, even if the scene is very challenging and difficult to predict. Thank you for watching.